So three things. So computation again is very, very fast, but the last thing is how to design distance. Okay. Maybe I will take 5 more minutes. Okay. Sorry? Oh, okay. Thanks. So then I think I should be fine. All right. So what I'll do is that I will explain the explain that sort of how potentially one might think about settings where distances are not known. It's a very special case where we know how to do things, but my hope is that sort of that provides insights in terms of how one might go about doing things even more generally. Okay, and I will so here's the setting. The setting is of matrix estimation. You saw that setting of matrix estimation in the Greg's talk. Potentially you will see again some variation of that in Yashi's talk later today. In case you don't, the Greg's talk and my talk don't do good justice, Yashi's talk will definitely do. No pressure. Okay, so here's the setup. So you have a data in the matrix form as follows. I have n rows, 1 to up to n. I have m columns, 1 to up to m. Okay. The entry ij is a random variable yij, which is my label just like as before. Okay. The way yij is generated as follows: yij is equal to some function, some nice function of a feature. Let's call it x11 to x1n. So these are the features associated with each row, and these are the features x21 to x2m. So these are the indices corresponding to column. This is index corresponding to row, row 1 to row n, column 1 to column n. So f of x1i, that is row i's feature, plus column j's feature, plus, let's say, Gauss, well, eta I should use. So, sorry, z, right? Yeah. So plus noise, and let's say it's Gaussian with mean zero, just to keep things simple, mean zero and variance one. These are independent, and let's say this is rho ij. Okay. So that's my noise, IID, and this is my function applied to the features, and that's my label, right? This is like nearest neighbor setting. It's just my x is a product, and let's say just to keep simple, let's assume that x1i, x2j are both in 0, 1, and even to keep things really simple, these x's, the features are chosen as per uniform distribution. That means that my px in our notation is nothing but product of uniforms over 0, 1. Okay. Setting is I've got features chosen uniformly at random on 0, 1 for each row, uniformly random or 0, 1 on each column. I have a nice function. Let's say think of Lipschitz function, like, or say C alpha equals to 1, 1, my holder function. And yij is nothing but this plus z. That is, this is my expectation of y given features, right? This is my regression function that I want to estimate. Okay, good. So what's the problem? Well, the problem is that in standard setting, I don't know this regression function which I want to estimate. I do observe this for some data points. Here, my problem is that I'm not going to observe the features. That is, I'm going to, while these things exist, I'm not going to tell you the features. Okay, I'm just going to tell you the indices. That is, these are the indices of columns, rows, and these are the indices of columns. Okay, and now I'll also sort of not reveal all of the entries, but that's besides the point, because again, still those are data points, and I can think of them as the data points that I observe. Question is that how do I do nearest neighbors? Okay. Now, if I knew features, so suppose, let's say I wanted to figure out this entry. Suppose I want to figure out this entry. That is, I want to figure out f of x11, x21. And I want to produce an estimation of that. Well, what I will do ideally is I will try to, in nearest neighbor, I will try to find other rows, let's say, where say suppose x1 x1 I1 to x1 Ik, these are such that they're very close to x11. Okay, let's say they're very close to x11 in L2 distance, and because I knew these features, then I can compute this distance. Then I will find these guys, those rows, and for those rows, I will find out what my y's are, which is y, I, j. Sorry, what am I doing? So this is column is 1, and row is ij. Summation over j equals to 1 to up to k, 1 over k, and that will be my good nearest neighbor estimate. Okay? Are we okay with that? Yeah. The only problem is that I can't find these guys because I don't know them, or I don't know them equivalently. I don't know the metric. Okay. So then, what to do? Well, so here is what people do in practice. They say that, well, you know, I want to sort of fill this entry. What I'll do is I'll look for all rows on the columns entries for which they're similar. I will use those guys and then to do that. Okay, so implicitly what they're doing is that's actually the answer, right? It says that, look, row 1 is a function which is x11 dot. Okay, row k is a function which is x1k, or let's use something else, row L, x1 dot. Okay, if these two functions are similar on few of the entries, maybe these two functions are identical or close to each other on all entries. And if that is the case, then I can sort of use the data from this row to do this. That means that maybe, and actually in principle, x's may be far from each other, right? I don't care because I care about prediction problem. For prediction problem, what I care about is prediction task, which means that this function or noisy version of this function value is the one that should be my right metric or for the purpose of this prediction problem. Okay. For purpose of some other prediction problem, it will be very different metric, and hence these two rows may not become different, same. So for example, I had another matrix with the same features, but function is g, but g has nothing to do with f. Maybe two rows will be different from each other. Okay. So that means that sort of what one would like to argue is that the distance between row I and row j, which I will define, let's say, as summation y il minus y jl square. Okay, and maybe if you want, you can normalize them too. Let's say this is total L entry. Normalize them. This is my distance proxy between rows. This is my distance between features for the purpose of this prediction. And now the claim is that, well, this all works out. This is the right thing. Why this is the right thing? Well, let's see. Let's just do one simple calculation, and then I will leave that there. Okay. So if you look at this quantity, right, and given that model, really this can be decomposed as follows. So you've got f of x1i, and let's say x2l minus f of x1j x2l, this square, plus a term containing these functions and the term containing the corresponding zetas. So functions and the zetas times 2, I'm just doing, and the plus a term containing zetas square. Okay, and all of them averaged. Summation here. And again, this is summation L 1 over L. Okay. Now, these guys are these are squares. So these guys are, if they're Gaussians, square of them are sub-exponentials. So, and they have, their mean is just sum of their variances because they're squares. So this will concentrate around its variance, let's say it's 1. Plus some error, let's say order 1 over square root of L, and if you like a little bit more for high probability. Okay. What about this one? Well, this is zero mean, and all of that will work out nice for the same reason. This is nothing but 1 over square root of L term. So this is square root of L. This is 1 plus square root of L. And what about this? Well, where is the randomness here? Well, the randomness is in this second feature, right? What if I sampled feature at random uniformly, right? So the mean of this is nothing but effectively L2 distance between these two functions. And now I'm taking the average. So again, what will this be? This will be effectively as I would write it, fx1I dot minus fx2I dot L2 square plus order 1 over square root of L term. Okay. Exactly same reason. Forget order square root of L terms. One is constant, so check this distances are shifted. Forget about that. So really, all that means is that this proxy distance is nothing but capturing the proxy between these two functions in L2 with respect to L2. Remember, these functions are Holder. So 2 in Lipschitz, 2 is same as infinity. Okay? So that means that sort of what we found these distances saying that if I find two rows which are close as per these proxy distance, I have found a row in these two functions that are close to each other in infinity norm. That means no matter what new index I'm going to choose, I choose this other guy, I'm going to get a good proxy. And that's basically it. All right, so what this suggests is, okay, so that's basically the argument, and okay, there's a little bit of cleaning up that one needs to do, but there is nothing more than that. Okay, so now the question, and in the popular term, this would say why collaborative filtering algorithm works. Okay, so one last thing, which is, all right, so now what about going back to our original problem? Even though I see features, I don't know the distance. How do I build distances? So here is my hypothesis, okay? It's a meta-hypothesis because it's not an algorithm. I'm going to build my distance, proxy distance as follows. I'm going to call it rho PRX K, okay? So for every X, I'm going to create my coordinates like this. So what am I doing? I'm going to say that I'm a point X. I'm going to find out all of my K nearest neighbors labels. I'm going to stack them up as a vector. And this will be my proxy coordinate. Now, of course, if I'm X, and if there is another X prime which is very close to me, hopefully my nearest neighbor and their labels would look roughly the same, right? Now, of course, there's a noise, so I shouldn't do L2 distance. But what I should do is I should do some kind of a cumulative distance, cumulative style distance to understand whether something is close or not. But hopefully there is enough signature in my local neighborhood through my labels that if X is close to X prime, then my labels in my neighborhood are close to my labels too. Okay. And again, in this case, what might happen is that underlying X and X prime might be far from each other, but for the purpose of the labels that I care about, they might be very close. And the example you want to think about is some kind of sinusoid like this. So X here is very close to X here. Okay. And hopefully something like this captures it. Now, I don't have an algorithm because I think it needs careful thought of how do you sort of translate from this coordinate to the right, let's call it distance. But this is very close to what's happening in this world too, right? You take the labels and then sort of you actually compute the distance between those labels. The nice thing was that columns were common, so that sort of helped. Here columns are not common. That is, here the distances from my nearest neighbor is not common. But of course, distributions concentrate nicely. So this type of things has to work out somewhere. K-dimensional embedding just for the purpose of this prediction problem. That is, depending on the prediction problem, my distance will change. And again, it has to be prediction problem dependent. Which one? That matrix? Sure, sure, you can do that. But sort of, if you have sort of a generic Lipschitz-Holder function, would it work? Well, it will work in some sense, assuming sort of you do sort of a little bit more refinements and so. Yeah, exactly. That is more importantly coming to this setup. It has to be task dependent, and this is how, in some sense, data. Yeah, so I think we are talking about two different. So you're okay. That is the matrix setup. There was analysis that works. We know that. Question is what happens in the going back to classical nearest neighbor setting. I observe the features, but maybe features are not the right distance, or are the right distance, but maybe my data is like this. I have such amazing periodicity. Why not I utilize that to actually get something better? Yeah. 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 So, so I think sort of, so it's okay. So one could say that maybe these are the features. That is in matrix factorization, you will do singular value decomposition, and you will say that sort of your singular vectors are features, right? Exactly. And so I mean, nothing really interesting to say, at least my end. Yeah. 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 Sorry, Cyril. Ah, yeah, yeah, yeah. So I think, okay, so I would say yes, because in some sense, y is your final observation, okay? So y is your final observation, but really the thing you care about is expectation of y given x. The expectation of y given x is maybe your true label, and actually y that you're observing is a noisy version of that label. All right. Well, there are a few other things that amused me while we were looking at this thing. Was there are these whole sorts of methods which are random forest or the tree-based regression methods or classification methods, and all of them implicitly are trying to learn some kind of a distance. Okay, so that has something to do with nearest neighbors, because after you do that, it's actually a nearest neighbors method, right? Because sort of you say, well, here's the partition you go, and then there's randomness. And those things have very similar structure to random partitioning trees. So clearly there are lot of things that are poorly understood in this domain. Random forest is a fantastic method that people use in practice. Yeah, nearest neighbors. I mean, everybody talks about deep learning, but then sort of logistic regression apparently the most used method out there. So question remains. Anyway, so I feel that sort of this is a really well old, a simple area, but there are lots of interesting questions out there. So worth spending some time over. All right, thank you. Okay, thanks.